This is quite an interesting device. I'm really looking forward to seeing what's in this. It's a generator automatic transfer switch, and this is a generic Chinesey one from eBay. And the brand is Thomson, and the seller on eBay was CGL 3478. And I've bought loads of things from them before, but note that because it's a generic imported product that doesn't comply with other standards in other countries, you have to be very careful in the applications you'd use it. It's one of these things that if you used it in a professional application and something went wrong, they could, well, delegate blame, since that's how industry seems to work these days. So the idea is, I should mention that this is to give you an idea of things that can go wrong, this is a clear MCB, and I got a few of these, I wanted to compare them for the size of the winding round the magnetic trip. And I noticed that the rating in the front is C32. Now, C is a tripping characteristic. It means it's rated for inrush current like inductive loads. And the 32 is its normal current rating. But it's got another rating here, 4,000 amps. And that is probably its short circuit breaking capacity. That's effectively based on, if you've got this on a distribution board coming into the house and you've got if you measure what's called the loop impedance, it basically measures the resistance of the conductors that go out from your distribution board to the substation and then back again. And based on those and the voltage, you can work out under extreme fault conditions what the current's going to be. And the circuit breaker has to be able to break it. So in the case of the UK, we're normally a minimum of 6,000 amps, but we also have 10,000 amp breakers to handle that, because otherwise the breakers could fail dramatically. So 4,000 amp is actually quite low. Now, the changeover switch, this is a manual changeover switch. And the idea is that if you can these are two pole breakers interlocked together. And if you turn one on, then when you try to turn the other one on, the other one will trip. And if you try to turn that back on, it will just click inside. It won't actually make the switch. And the only way you can get this one back on is if you turn this one off and then turn this on. And the idea is that your main supply is coming in through one of these breakers and your generator supply is coming in through the other. And then they're being either fed to different boards or more likely combined on the output. And the idea is to stop you backfeeding from your main supply to the generator. And this is important for a couple of reasons. The one reason is the size of the bang it would make, and it wouldn't do your generator much good. But the other one is a safety thing. You see, if you, and this is commonly done in America, if you have a house, there's a very crude drawing of a house, and you get a power cut, and the power's coming in, it's coming in from the local utility pole with a transformer on it, and then from there, you've got the 11 kV transmission cables, or kind of 11 kV is more sort of like a sub-distribution voltage before it steps down to your low voltage. But you've got the generator outside, and you have the power cuts, you take a lead into your house, and a really common thing is for people to take dryer leads in, the plug for the outlet for the dryer. And literally on the end of the generator, the live output of the generator, they've got a plug. And that's what we call a widowmaker in the entertainment industry. So you often find these leads that have been made up by people who just didn't know. And the risk there is that if you handle that plug, you're going to get a shock if the generator's running. But what they do is they hopefully turn the power off at their distribution board, and then they backfeed their whole electrical system in the house by plugging that into the dryer outlet in their laundry room, because it's the highest current connector, and it also lets them power both phases in the American system. The downside of that is, if you actually leave this turned on, or someone who doesn't know what they're doing goes and says, "Oh, that's the power on, I can see it," and turns it on, you could basically connect the substation transformer on the pole down to or pole transformer is a better description, or substation transformer to your generator, and one of them is going to have a bad experience. But worse still, if you've got a cable down and there's someone actually working on the restoration of the power, then if you backfeed into this transformer, you can actually step the voltage up, and you can end up with thousands of volts on the overhead lines because it's stepped the voltage up. And the people working on it are actually at risk of fatal electrocution if you do that. And this has happened. It has happened quite a lot, where people have been working the lines and suddenly they convulse up because someone has backfed the line from a generator. So you have to be very, very careful in that approach. And the utility industry is also, they're changing the regulations. They're making linemen ground the overhead lines even if they know they're dead, just because this sort of stuff is happening. But this device is designed to kind of protect against scenarios like that, because it allows you to bring your normal feed in here from the utility company. It allows you to bring the generator feed in here, and the output can then be combined to go to the distribution board. And the good thing about this thing is that when you power it up, normally, let's move this across to here. Say, for instance, your main supply is there. I'm going to have to be careful, this is all 240 volts. Then the switch is in this position. You can bypass it, you can turn this off, and you can manually switch it over to the other side. But when you turn it back on, it will automatically wind back over and activate the circuit breakers on this side to put the feed through. However, when the power fails and the generator supply comes on with this clear plug, the power will automatically transfer over. And an indicator light will come on. It's not just an indicator light. This could be used to control systems that monitor the power. But typically this would be a front panel indicator to show which service was in use. And if the mains power then comes back on again, because it has priority, it will wind back over and give that priority even if the generator is still running. It's just a means of quickly changing over. And ultimately then at that point, the generator system could go off automatically, or it could be turned off manually. Some other systems, particularly in the entertainment industry, if something fails and it goes to the generator, then the only way you can change it back is manually, because the last thing they want is intermittent power coming on and trashing all the sort of lighting system until they've got a stable voltage. So generally speaking, in the case of the entertainment industry, it's programmable on the generator itself what's going to happen, and that is usually just revert to generator power and stay there until further notice. This one is very simple. It's just one or the other depending on what power is available. Quite neat. Now, I did notice that if you unplug things, you can hear relays clicking inside. Let me do this. I think this is all based entirely on relay logic inside, and that makes sense. There is no connection from the input, the generator input, to the normal input to the generator input. I've checked that with test lamps. I've also metered it through. It does completely keep isolation. So I'm guessing that each of these inputs will be feeding a relay, and the relays will be will be wired to be interlocked. I'm also wondering what sort of protection there is in the case of a fault occurring with the motor or the relays in this, because there's quite a big motor sticking out the back. It draws about, it happens so quickly it's hard to measure, about 70 watts when it's changing over. So let's disconnect these leads and make sure they are unplugged before I disconnect them, and we shall open this and take a look inside. So I'm going to throw these leads out the way at the moment, so I don't do anything silly. Not that it ever stops me from doing anything silly. I would also like to say I've actually already had a slight bang off this, because it's obviously got capacitors inside, because I got a good zap off that earlier on when it was unplugged. So things I'm noticing here are that there are little tabs on the circuit breakers with soldered connections. And likewise in the input, there are soldered connections coming off each of these. Not seeing an obvious way to open this. It looks like this cover should come off, but it doesn't. I don't know how they're interlocked. Hold on, let's get a pair of long-nosed pliers and just grip that and see if I can encourage this to come off, or am I going to end up destroying something? I don't want to break this. They seem to be quite well interlocked. Not sure they're interlocked. Right, I also noticed that this main cover is stopped from coming off, possibly. Well, a contributing factor will be this knob here. So I'm going to, I notice there's a screw hole under here, so I'm going to get the spudger and I'm going to remove that label carefully, or not carefully as the case may be, and see if there's a screw under there. There is a screw under there. Okay, let's put that out the way, that label, and undo that screw. let's see if I can chew everything up in the process. So, I was going to say I don't know what these are rated at, but here's the thing. Model TOQ363, I think that is 63 amp breakers in this, but we'll find out when we get it out, because we can investigate that. So that's that knob off. There is a screw here, that's helpful. Yes, I'm probably using the wrong type of screwdriver here. I do that quite a lot. Torx versus, not Torx, posi drive versus, oh, that's promising, that's promising. Ooh. Posi drive versus Phillips, that's quite neat, isn't it? Oh, and now that whole mechanism just drops off. What about these? Are these going to pop out now? What is holding these in position? I think they're interlocked in some way with these plastic tabs down here. Oh, I kind of want to power it up now and see this mechanism run. Oh, and I've disconnected it, but then that's never stopped me before. Right, let's say I get these covers off. Oh, I see some screws here. Is this going to do anything, or is this just going to suddenly make everything fall apart? So the motor is rated 0.5 amp. I think it's only rated for short duty use. Oh, it says 8 watt. Yeah, that was accurate then, the 7 watts I was seeing. Quite a powerful little motor. Is that going to come off because I've done that? I don't think it is. I think I'm onto plums here. I'm going to have to work out another way to get this off. How are these? Gripped. Oh, there we go. There we go. In which case, I think these can actually stay put, so I'll pop them back in before I destroy everything. Oh, this is quite neat so far. I'm liking this inside. I can see a capacitor. I can see positive temperature coefficient thermistors as well, by the look of it. They might be fuse protection. I'm not sure. I'm just seeing kind of one motor, one relay here. Maybe it is just one relay. Let's get this other thing off. These things do just seem to clip under at the bottom. So if I grip this at the bottom here and pull, yeah, that's how they come off. And at that point, theoretically, you could put in new breakers. But of course, these ones might be special, or, oh no, they've actually just soldered onto the top of the clamp where the rising clamp comes. The LEDs on the top are just resistors by the look of it. And one of the connections to each of those LEDs, of the output lamp indicators, comes from the switched output here. The other side, it probably comes from the input. There is no electrical connection between the outputs, again, as far as I know. It is each light is fed from its own particular supply. So there's a connector there. Is that going to come out, or is that kind of like, oh no, I think it might be hot melt glued to stop it popping out. Oh, these are kind of glued in. There's the motor connector, which is also clipped in quite tightly. God, everything's just really tight. Tell you what, before we go any further, let's actually take a look at this mechanism. And to do that, I'm going to have to get a lead and power it up again. Let's apply 240 volts and get this mechanism to operate. So I'll put it onto the main master side. Oh, am I going to be able to actually do this? Let's see, that one is actually on at the moment, so before I plug it in, I'm going to have to bypass it so it goes like that. Okay, let's see what happens when I plug it in. See if it goes bang. Okay, that's reasonable enough. So what's the sequence of operation here? It starts off by tripping this one and then setting this one. So there is a distinct time delay. There's no point at which they're both connected at once. As soon as that starts turning, it will trip that one. I wonder what the click was. God, that's quite hard, because that'll be why it's a strong motor. It actually has to trip that. That is quite a powerful arrangement. That takes a lot of force. Let's do it again electrically. Oh, that's quite good. I wonder what happens if the motor stalls and keeps running. I do see positive temperature coefficient thermistors down here that are probably going to resolve that. I wonder why the relay has got a little satellite circuit board. Oh, that's so they can mount it sideways to take less space. The capacitive dropper. Oh no, it's not a capacitive dropper. That capacitor, the bit that I got a nip off most likely, is to do with the motor. Because the motor has 3 connections going to it. One will be, it'll have 2 windings, and depending on which one you put the capacitor in series, it causes the rotational difference in the phases, and that's what determines the direction of the motor. And I'm guessing that the motor, these contacts will go back, these switches here, do go back to the board, and they will automatically then disconnect the motor depending on the direction that it's actually running in. So that's quite interesting that they've got it down to a single relay. I was kind of expecting 2 relays, and the relay is powered, by the sound of it, from the input to here, from the main input, because it takes priority. And when it fails, it will then connect, the relay will cut out to the other position, and it will then, now let's see, yeah, it will then connect to the supply from this, which will then be able to drive the motor in the other direction. It's interesting. Kind of tempted to doodle that out now. Yes, I think I'll have a wee doodle. Oh yeah, let's just reverse engineer it, says Clive, thinking that's going to be easy. So, 2 hours later, 4 cups of tea, 2 gin and tonics. Okay, to be honest, 1 gin and tonic, and the second one is here for celebration purposes, and the remnants of a packet of tortilla chips and dip, and finally it is reverse engineered, and by far the worst bit was getting this relay out, because the relay was on this little satellite double-sided board, and when you've got the relay contacts, well, let's do it on that bit of paper down there. When you get the relay with the contacts come out, they come these little metal tabs with the pin that goes through the circuit board. It had been put up so tightly that the solder had not just gone on the pin, but actually so flooded all around those connections there, which meant it was very hard to desolder. And after a lot of attempts and different techniques for desoldering, I ended up using a bit of brute force instead, and this is now toast. But that's okay, it could be rewired if I desired, just by hardwire links. And it's a very clever design. It's very, very optimized. Very smart indeed. So the mains, the generator and the mains live both go through these positive temperature coefficient thermistors, these solid state fuses. But they also go through a little arrangement, which I've not actually drawn on the drawing here. I'll just doodle it on right now. Strangely, it bypasses the protection completely, but there's a little resistor there with an LED, and then 2 mains neutral, and it does the same at the generator side, and those are 150k resistors. It's a common cheating technique to do that. It's a bit, the resistors will get warm. They'll just be about just under half a watt, which is, they're half watt resistors. It's within their rating to be just under that. But it's clever because the relay coil is connected basically across mains live and mains neutral. And that means that whenever mains is there, the relay is pulled in. And I've shown all these contacts, all these, the relay contacts here in their pulled in state. So let's start off with let's start off getting the neutral side out the way. All that happens is that the motor's common, which is also, that's another thing I've not shown. This switch that turns the motor on and off is actually in there. So it can actually take control by just disabling the motor completely. So when it's powered, the motor's common neutral is connected to mains neutral, and when it's not powered, it drops down to the generator neutral. There's a clever arrangement here. They've got two commons connected together on two sets of the relay contacts. There's three sets of contacts, changeover contacts in all. And when it's connected to the mains and the relay coil pulls in, it basically bridges across from mains live to this contact of the limit switch for controlling the motor. And by using that common contact, it means that it completely isolates it from the generator. This lets the two sections of circuitry stay completely separate because you don't want any bridge between the... that's a good demonstration of it there. You don't want any connection between the generator live and the mains live. So there is effectively a complete clearance path all the way through here that just separates the two sides. When the coil is on and the motor's to run in that direction, this is at one of the limit switches. It's the end of travel switches. And initially, if the motor isn't in the right position, it will power the motor via this connection here. And the motor has two windings and a capacitor across them. Whichever one you connect, that winding will be on the sort of mains waveform, but the other one will be through the capacitor, so there'll be a phase shift. So the motor will run in one direction. If you were to connect this one to live, this winding would be on the mains waveform and the other one would have the phase shift through the capacitor. So the motor runs until that switch changes over, and when it does, it not only disconnects the motor at the end of travel, but it also powers up the indicator light in the output. That's the thing that I had these indicator lights connected to, plugged in. It also has a resistor again and an LED for each of those output stages, which, is that visible? Yeah, that's the indicator positions there. The LEDs stick through here, and that terminal block goes in here. So that's the indicator light position and the little resistor and LED across it. When the mains is turned off, the relay contacts just drop down. But if there's no power there, if the generator is not active, then nothing will happen. But as soon as the generator becomes active, then because the relay is in the other position, it powers it via this other end of travel limit switch, and the motor runs in the opposite direction, and it just winds round until it's flicked over the circuit breakers, and then of course it switches over and it indicates on the output with the indicator lamp that it's in that generator position. You know, it's so simple to describe, it's relatively simple to read the schematic, but to actually reverse engineer it took a lot of time, particularly with those hidden contacts, particularly because of that little bridged thing there, which couldn't easily be measured from the edge contacts, and the fact that the relay contacts were in a one state and it was kind of giving misleading readings. So it's actually really clever. If you look at this circuit board, it is anti-tracking slots between everything. It's like a really seriously functional design, and it seems perfectly acceptable, to be honest. These circuit breakers don't have any markings on them as such on the top. There's no printing on them at all. I don't know what the rating is. I wonder if they've got some code somewhere in it. No, I don't see a code on them for what their rating is. Are these overload devices? Or, oh, look at that. You can actually, if you manually push up, you can get both on at once. But that's never going to happen just because of the way the mechanism works. So I wonder if the rating, I wonder if these have an overcurrent protection as well, or they're just purely switches inside. I'm not sure. But, yeah, it's a robust mechanism. It's a very simple mechanism. The design is super optimized for this relay, and I like the fact that the motor direction capacitor is on board, and the circuit board is really, really empty. There's so little in it. The only niggle I've got is that the relay coil is just energized all the time, so I wonder how reliable that would be, because if it cut out, effectively, it would just remove the automatic mode from this. You could still operate it manually, but it wouldn't do the automatic transfer thing. But that's interesting. That was very interesting. I quite enjoyed it, even if it took somewhat longer than expected. And it is a nicely made device. I've given it a bit more thought, and what would actually happen if the relay coil failed is that the relay would drop into its generator position, and nothing would happen initially. It would stay in mains mode. But when there was a power failure, when the generator started, or even if the generator started while there wasn't a power failure, it would then suddenly do the transfer over to the generator. The generator would take priority. And when the generator was stopped, even if the mains had recovered or it hadn't even been turned off in the first place, you would have to turn it back manually. It wouldn't be able to actually wind back to the mains position. So that's an interesting thing to note if you had something similar fail. Another thing I want to mention, I checked the listing and it said these are 63 amp MCB. Is it 63 amp? Yep, 63 amp MCB type. Given that these are not marked, I know they don't have to be marked because they're application, but there's no knowing if these are just an isolator or they've actually got overcurrent protection. I think as a precaution, if you're using something like this, I'd provide external protection as well, just an extra 63 amp breaker. Now look at this. This is the manual device that I showed at the beginning where when you turn one on, it kicks the other one off. And this one then won't latch until the other one has been turned off again. Aside from the fact I noticed this is a 3000 amp breaking capacity, which is worse than the other one. But this one, if you're ever using something like this, instead of actually relying on when you turn this one on of the other side being kicked off, I'd always recommend turning both off and then turning the other one on. It's a good practice to get into because, a good style, because if something failed and you actually did manage to get both of these up together and connected, then you'd be connecting the mains to a generator and they'd almost certainly be out of phase and it could cause a lot of damage and possibly quite a loud bang as well. So it's always a good precaution to turn off and then enable the other one. Just get into that habit.